Energy transfers. Reading guide. Key concepts. Essential questions. What is the effect of having a small specific heat? What happens to a material when it is heated? In what ways can thermal energy be transferred? Vocabulary. Radiation. Conduction. Thermal conductor. Thermal insulator. Specific heat. Thermal contraction. Thermal expansion. Convection. Convection current. Inquiry. Keeping warm? Imagine camping in the mountains on a cold winter night. Your survival could depend on keeping warm. There are many things you could do to get warm and stay warm. In this picture, how is thermal energy transferred from the fire to the camper? Why does his coat keep him from losing thermal energy? How is thermal energy transferred? Have you ever gotten into a car, such as the one in Figure 6, on a hot summer day? You can guess that the inside of the car is hot even before you touch the door handle. You open the door and hot air seems to pour out of the car. When you touch the metal safety belt buckle, it is hot. How is thermal energy transferred between objects? Thermal energy is transferred in 3 ways: by radiation, conduction, and convection. Radiation. The transfer of thermal energy from one material to another by electromagnetic waves is called radiation. All matter, including the sun, fire, you, and even ice, transfers thermal energy by radiation. Warm objects emit more radiation than cold objects do. For example, when you place your hands near a fire, you can more easily feel the transfer of thermal energy by radiation than when you place your hands near a block of ice. Thermal energy from the sun heats the inside of the car in Figure 6 by radiation. In fact, radiation is the only way thermal energy can travel from the sun to Earth. This is because space is a vacuum. However, radiation also transfers thermal energy through solids, liquids, and gases. Reading check. How does the sun heat the inside of a car? Conduction. Suppose it's a hot day and you have a cold glass of lemonade, such as the one in Figure 7. The lemonade has a lower temperature than the surrounding air. Therefore, the particles that make up the lemonade have less kinetic energy than the particles that make up the air. When particles with different kinetic energies collide, the particles with higher kinetic energy transfer energy to particles with lower kinetic energy. In Figure 7, the particles that make up the air collide with and transfer kinetic energy to the particles that make up the lemonade. As a result, the average kinetic energy or temperature of the particles that make up the lemonade increases. Since kinetic energy is being transferred, thermal energy is being transferred. The transfer of thermal energy between materials by the collisions of particles is called conduction. Conduction continues until the thermal energy of all particles in contact is equal. Thermal conductors and insulators. On a hot day, why does a metal safety belt buckle in a car feel hotter than the safety belt? Both the buckle and safety belt receive the same amount of thermal energy from the sun. The metal that makes up the buckle is a good thermal conductor. A thermal conductor is a material through which thermal energy flows easily. Atoms in good thermal conductors have electrons that move easily. These electrons transfer kinetic energy when they collide with other electrons and atoms. Metals are better thermal conductors than nonmetals. The cloth that makes up a safety belt is a good thermal insulator. A thermal insulator is a material through which thermal energy does not flow easily. The electrons in the atoms of a good thermal insulator do not move easily. These materials do not transfer thermal energy easily because fewer collisions occur between electrons and atoms. Specific heat. The amount of thermal energy required to increase the temperature of 1 kilogram of a material by 1 degree Celsius is called specific heat. Every material has a specific heat. It is easy to change the temperature of a material with a low specific heat, but hard to change the temperature of a material with high specific heat. Thermal conductors, such as the cloth of the safety belt buckle in Figure 8, have a lower specific heat than thermal insulators, such as the cloth safety belt. This means it takes less thermal energy to increase the buckle's temperature than it takes to increase the temperature of the cloth safety belt by the same amount. The specific heat of water is particularly high. It takes a large amount of energy to increase or decrease the temperature of water. The high specific heat of water has many beneficial effects. For example, much of your body is water. Water's high specific heat helps prevent your body from overheating. The high specific heat of water is one of the reasons why pools, lakes, and oceans stay cool in summer. Water's high specific heat also makes it ideal for cooling machinery, such as car engines and rock-cutting saws. Key concept check. What does it mean if a material has a low specific heat? Thermal expansion and contraction. What happens if you take an inflated balloon outside on a cold day? Thermal energy transfers from the particles that make up the air inside the balloon to the particles that make up the balloon material and then to the cold outside air. As the particles that make up the air in the balloon lose thermal energy, which includes kinetic energy, they slow down and get closer together. This causes the volume of the balloon to decrease. Thermal contraction is a decrease in a material's volume when its temperature decreases. How could you reinflate the balloon? You could heat the air inside the balloon with a hairdryer, like in Figure 9. The particles that make up the hot air coming out of the hairdryer transfer thermal energy, which includes kinetic energy, to the particles that make up the air inside the balloon. As the average kinetic energy of the particles increases, the air temperature increases. Also, as the average kinetic energy of the particles increases, they speed up and spread out, increasing the volume of air inside the balloon. Thermal expansion is an increase in a material's volume when its temperature increases. Thermal expansion and contraction are most noticeable in gases, less noticeable in liquids, and the least noticeable in solids. Key concept check. What happens to the volume of a gas when it is heated? Sidewalk gaps. In many places, outdoor temperatures become very hot in the summer. High temperatures can cause thermal expansion in structures such as concrete sidewalks. If the concrete expands too much or expands unevenly, it could crack. Therefore, control joints are cut into sidewalks, as shown in Figure 10. If the sidewalk does crack, it should crack smoothly at the control joint. Hot air balloons. How do hot air balloons work? As shown in Figure 11, a burner heats the air in the balloon, causing thermal expansion. The particles that make up the air inside the balloon move faster and faster. As the particles collide with one another, some are forced outside the balloon through the opening at the bottom. Now there are fewer particles in the balloon than in the same volume of air outside the balloon. The balloon is less dense, and it begins to rise through denser outside air. To land a hot air balloon, the balloonist allows the air inside the balloon to gradually cool. The air undergoes thermal contraction. However, the balloon itself does not contract. Instead, denser air from outside the balloon fills the space inside. As the density of the balloon increases, it slowly descends. Oven-proof glass. If you put an ordinary drinking glass into a hot oven, the glass might break or shatter. However, an oven-proof glass dish would not be damaged in a hot oven. Why is this so? Different parts of ordinary glass expand at different rates when heated. This causes it to crack or shatter. Oven-proof glass is designed to expand less than ordinary glass when heated, which means that it usually does not crack in the oven. Convection. When you heat a pan of water on the stove, the burner heats the pan by conduction. This process, shown in Figure 12, involves the movement of thermal energy within a fluid. The particles that make up liquids and gases move around easily. As they move, they transfer thermal energy from one location to another. Convection is the transfer of thermal energy by the movement of particles from one part of a material to another. Convection only occurs in fluids, such as water, air, magma, and maple syrup. Key concept check. What are the three processes that transfer thermal energy? Density, thermal expansion, and thermal contraction. In Figure 12, the burner transfers thermal energy to the beaker, which transfers thermal energy to the water. Thermal expansion occurs in water nearest the bottom of the beaker. Heating increases the water's volume, making it less dense. At the same time, water molecules at the water's surface transfer thermal energy to the air. This causes cooling and thermal contraction of the water on the surface. The denser water at the surface sinks to the bottom, forcing the less dense water upward. This cycle continues until all the water in the beaker is at the same temperature. Convection currents in Earth's atmosphere. The movement of fluids in a cycle because of convection is a convection current. Convection currents circulate the water in Earth's oceans and other bodies of water. They also circulate the air in a room and the materials in Earth's interior. Convection currents also move matter and thermal energy from inside the sun to its surface. On Earth, convection currents move air between the equator and latitudes near 30 degrees north and 30 degrees south. This plays an important role in Earth's climates, as shown in Figure 13.